Alright, let's continue. Okay, let me open the table of content first. We are on chapter 18, still on chapter 18, and still on homework simulation. Let me open that. Okay, we are in this section. We had to take a look at question 1, question 2, and now we are in the question 3. I am still not sure how to, what is it called? How to determine the offset, I guess. Let me open that. So let's take a look. Where is it again? It is in the Patching Linear Translate. Okay. Patching Linear Translate here. And patching Linear Translate with this flag. Can the test you I missed the mosquito. Okay, the test you in here is the percentage of the virtual address space that is used. So if we provide 0, it means 0% is used. And if we put the 25 here, it means 25% is used, something like that. I think this one. Okay, how to read the X number from page table. Yeah, that is one of the questions that I need to answer. Wait, test P on K. I think test P is, yeah, it is page size. Okay, the page size is 1K, and then the address space size is 16K. And then the physical memory size is 32K. We add verbose flag, and then the use flag, or use percentage flag, maybe something like that, is 25. So I'm kind of curious about this one. Like, how do we read this? Let me check. Oh, this one. Page table from entry 0 down to the max size. Okay, let's take a look. Okay. Page. Okay, so I assume this one is physical memory size. Okay, this is physical memory size divided by page size. Okay, so let me put that information here. Right? Okay, this one, right? 32. Okay, divide by 1k. Be something like that. But then, what is it called? I think no, not that one. How many bit is 32k? I mean in the binary format, something like that. If we have something like this, okay, 16 bit. Oh, less than 16 bit. Okay, 14 bit is 16. Okay, and then okay, 15 bit. It looks like. Alright. So we have this divided by, what is it called? Oh, wait. Okay, 32. Is there any? Okay, no. Yeah, the mosquito distracting me again. Alright. So we have 32 pages. Here. Now assign some bits of the virtual address. Okay. Alright, must be power of 2. Okay. And this one is just checking. Okay, page speed. Okay, virtual page number page. Virtual type speed negative page number page, and then doing some left shift -1. Okay. Virtual page number bits. Okay. curious about this one. How to read this? Okay, bits, and then random, I guess. If is equal 0, okay. Wait a minute. Array I. Why import is in the middle of the code here? Okay. Alright. Use wait. Does this mean if what is it called? Okay, does this mean if it is 0%, we will do this. Let me check, I guess. No. Interesting. Okay. Array. But what? What is this? Wait. Why? Oh, here's insert. Okay. I'm assuming this is integer, maybe something like that. Let's try this one. Wait a minute. Is it only appear? Okay. That is interesting. Float option use. Alright. this is printing out what is it called? The valid one maybe rather than invalid. Maybe. Okay. Oh yeah, this is not valid. Okay. Thing like that. Okay, verbose to page here, this one, virtual page, okay, address, the address space is here. Divide by 16. Okay, right. So you have 16 virtual page here. And this is invalid. Oh. So wait a minute. Let me, oh yeah, not that one, hex to decimal converter. Yeah, at some point I need to learn how to read the hexadecimal number. Oh yeah, let's swap this 24 maybe 18. Oh, okay. So okay, at 24. Alright, so I assume this one is the, what is it called? The hexadecimal number that we need to read, right? 10. Okay, the hex number is 13 here, right? 31. Oh, hex sign to complement for digit. Okay, maybe we need to read this, the 4 character, what is it called, the 4 character at the end. Maybe, well, I'm still not sure. Okay, I'm still figuring things out here. Okay, 1C. Alright, and then how do we decide this one? Zero, 3, okay. 3, 9, maybe 3, 9, x6. Alright. If we remove 3 here, not that one. Not available. Oh, is this the, what is it called? The offset, maybe something like that. Okay. Let me check again. To translate this to virtual address into physical address, we first have to break it up into Esconti. To translate this virtual address into a physical address, we first have to break it up into its constituent components, virtual base number and an offset. We do this by noting down the size of the address space and the bit size. Okay. This example, the address space is set to 16K, and then the bit size is 4K. Thus we know that there are 14 bits in the virtual address. Okay, 14 bits. Okay, 14 bits is from this one, I think, right? So the address space is 16K, and then this one is the, what is it called? Is the bit, alright. And then that the offset is 12 bits. Okay, yeah, I mean, not that one. Yeah, this is, oh, wait a minute, 12 bit is the offset, and this is 4 kilobyte. I mean, we know that this one result in 16k. Is this one? No. Okay, this one, the 12-bit is the bit size. Okay, the offset is 12 bits, leaving 2 bits for the virtual bits number. I think the offset in this case means that what is it called? The size of the bits, maybe something like that. The size of the bits is, what is it called? Is the bits, maybe something like that. Offset is the bit size bits, question mark, and then the virtual bits number is the rest, maybe something like that. Virtual bits, yeah, let's virtual bits number, maybe the address base size minus the offset, something like that. Oh, hello Jeffrey, welcome. We are still reading this book, Operating System 3 Easy Piece, and currently on chapter 18, learning about patching, the introduction of patching here, and currently trying to analyze the simulation script, like how do we read the hexadecimal number or something like that. How do we read this information from the script, like this address, what is it called, this this address number, maybe something like that. And then how do we determine the offset, okay. If the virtual base number, okay, those with our address, this one, it is binary. Okay, we know the top 2 bits specify the virtual base number. Okay, thus this address is on virtual bits 3 with an offset of this one. Okay, I mean previously we also already what is it called, already taking a look at the virtual page number, how to decide the virtual page number. For example, this one, yeah, maybe I should put this in here. 3986. The virtual page number is this one, right? Sorry. This is the virtual address in decimal format, and then we need to find where is this number exists in this physical, in this, what is it, in this page entry reside, maybe something like that. And this is in this page entry, so it is virtual page number 14. And yeah, I am still not sure about the offset. Okay, if we take this one, we got this. Are this the offset? I mean, the page number is, the page size, I mean, 1K. If my hypothesis is correct, is the page size bits? Let me check. Okay, 500. Interesting. Yeah, can we just do this? Okay, wait a minute. And because it is this one, right? Page number 14, it is invalid. To PC6 virtual page number. What is it again? 11206. Okay, I think in this one is number 10. Number 10, there is this one. How do we get that? PC6. Is that it? How do we calculate the physical address with the offset? mean, if I put this one, I think this is more than the physical memory size, right? So yeah, I am still not sure how to calculate this. FC for FC6. For FC6, I mean, yeah, let's try this. Okay, 9K. Let me look at this one. Split virtual address into virtual page number and offset. Okay. Let me print that, I guess. Alright. Let's add this here. Okay, 966. 966. Let me try. Three C6. Like what? Three C6, not 2P6, not PC6. Okay, interesting. Okay, or maybe this one that we need to take. Is there any binary? Okay, there is. Hmm. 3014. Okay. Okay, PC6. Okay. Looks like the patch marks here change the offset, I guess. Okay, patch marks. One 2023. And then what about, okay, alright. Oh wait, not that one. Wait, Oh, okay. Does that mean we need to know the patch marks to get the offset? Decimal, not decimal to decimal, decimal to binary, I guess. Okay. So, alright. Interesting. Oh, wait a minute. Is patch mark depends on the patch size here? Let me try changing the patch size. Okay. Okay. Everything is invalid. Alright. Okay. Looks like the patch mark is the patch size. Okay. Patch mark, patch size. Patch size 1. Okay. Something like this. Patch marks. Yeah. Sorry, I mean patch size -1, maybe something like that. And then the offset is virtual address. What is this bit operation again? Again, I forgot. Something like this. Okay. Yeah, let's use equal sign here. Bitwise operation and Okay. Alright. Oh. Okay. Okay. A shift left by end position. Okay. Speed from X is flip. Oh, interesting. Wait, let me put this in the chat in case anyone wants to take a look. Okay. Bitwise or corresponding bit in X and Y. Wait a minute. This one. Its logical counterpart. If either the operands are true, otherwise it evaluates to false. Either. Okay. However, whereas logical OR is applied to the entire operand, to produce a single true or false result, bitwise OR is applied to each pair of bits in the operand. Produce a single true or false result for each bit. Applied to the entire operand is applied to each pair of bits in the operand. A single true or false result for each bit. Okay, we have this one. By hand, it is easiest to line the two operand up like this. Okay. Then apply the operation to each column of bits and write the result underneath. Okay, this one 0 and then this one 1, I guess, and this one 1, and this one, the last one is 1. Oh, okay. Okay, at least what is it called? One of the two need to be 1 for it to result in 1. Okay. Works similarly to the above, except it uses AND logic instead of OR logic. For each pair of bits in the operand, bitwise and set the resulting bit to true if both pair bits are 1 and false otherwise. Okay. Right, this is 0, this is 1, this is 0, and then this is 0. So both of these need to be 1. Something like that. Okay. assuming the offset is in the binary representation, maybe something like that. Hexadecimal. Oh, maybe decimal. 11, okay. This is the binary. And then okay. Yeah, maybe the X marks here is the, what is it called? The largest number in the page, I guess. I mean, assuming we have this one, the page size 1024, so it will be 0 until 1023. So maybe this is the page marks or something like that. Maybe a big question mark there. Oh, wait a minute. Maybe I should put this one. Okay. Right. Okay. Now let's try calculate this with n. Okay. Okay. All right. Let's see what is the result. Okay. What is this again? And then this one is okay. And bitwise operation. This one is okay. So we got the offset here. Alright. Let me put this in the info here. Yeah, I'm still not sure how to there is the hex number there. But for this one, I think we found how to do that. At least in this, what is it called? In the simulation script. Okay. Example calculate. What is it called? Calculate offset. Okay, maybe something like this. It's correct, right? Okay. Alright. find out the offset, and now oh right, I need to change the bit size to 1K again. How to add that? Okay, what is the bit speed here? Let me print that. Bit speed 10. Okay, bit size divided by 2. Oh, wait a minute. Something like this. But look. Method lock. Logarithm of different number. Oh, okay. Alright. Can we do this? Alright, we need to import that. Oh, interesting. Float. Oh, this is also logarithmic. Okay. Yeah, I'm kind of. Why is this need to be float? Because the logarithmic is float, I guess. You know what? Let's try this and change the bit size to 4. Wait, what? Is it because I'm using this? No. What is the difference here? This is this is interesting. Okay. Let me try a case. Oh, okay, yeah. I can see the difference now. Alright, yeah. It's not like this. The what is it called? The logarithmic only, what is it called? Only one component, I guess. Right, okay. Alright. Mystery solved. Okay, yeah. There are two logarithmic here, and we divide those two logarithmic instead of doing logarithmic for the division, I guess. So there is that. Okay. Yeah, why we need the logarithmic here? That's what make me curious, I guess. Okay. What about 96, 12? Oh. Why do we need to use logarithm for calculating bit speeds? Okay. Bit speed 10, and then or offset. Okay. Wait a minute. I'm also kind of curious about the page frame number here. Okay. 19. 19 and then left shift. Page speed. So maybe something like this. And then or the offset. What is the offset again? 966. Oh. Okay. Yeah, what? Why do we need to left shift? Oh, do we need to? I think I need to have some breakfast after this. Okay, to left shift. Why do we need to left shift the page frame number? With page speeds. think in the book there is some explanation there. Or okay, let's put this in the new question. We need to use our bitways of after save page frame number with page speeds. In this case, might as well asking, why do we need to use the end bitwise operation for the offset? And bitwise operation between what is it called? Virtual address and it's page max. It is page size -1. Yeah, I have a lot of questions. I'm not sure if I can answer that. Okay. I guess we will continue this on the next session and see if we can find some of this question. We can find the answer to this question. Alright, that's it for now. Thank you for watching and see you next time. Bye bye.